Hello everyone. I am Shreyas Ashok Pawar from Government College of Engineering, Karad. Today I will be presenting my presentation of our EV dashboard and ADAS warning system internship in Emertxe Technologies. Our project is in domain of automotive embedded systems and EV telemetry ADAS system. In this project, we have some project requirements and system objectives such as real-time telemetry data, which means our system should collect the real-time data every 10 millisecond, and our heart of the system, which is STM32, should process it and forward the data to the dashboard. After that, the next requirement is speed estimation, which means our system should calculate the speed of the vehicle based on physical inertia parameters. The next is range prediction. Our EV should be able to predict the range remaining range of vehicle which it can travel based on the state of charge. After that, the system should generate ADAS alerts, which we will see further. The components and hardware integrations which we are used here are STM32 microcontroller, which is brain of our system. It controls all the input and output operations. STM32 we have used at 10 millisecond intervals. We have generated interrupts by using timer and counters in programming. After that, we have used ultrasonic sensors to get the values of distance in the front of vehicle left and in the right of the vehicle. After that, we have used the potentiometers to get to simulate the values of acceleration, speed, motor temperature, and SOC. We have used a 12-bit ADC between potentiometer and STM32 so that STM32 microcontroller can read the analog values converted into digital. We have also used LEDs for actuation of signaling the warning indication. The next is vehicle states. So we have used various vehicle states in our EV. So the first state is parked state when the acceleration is 0 and the brakes are 100%. After that, if we increase the acceleration and reduce the brake percentage, the vehicle will be in ready state. When we increase the acceleration further, the vehicle will then move into the driving state. In the driving state, if we increase the brakes, the vehicle will go into regenerative state, and if we do not apply the brakes, the vehicle will go into the driving state again. During this, we have also implemented fault detections. So there are various reasons for the faults such as motor overheating, SOC range very less, or collision occurring. During any of these situations, the system will detect a fault and alert the user. The next is ADAS features. So ADAS should be able to detect the blind spots near the vehicle and alert the driver or passengers. After that, we have used the parking assistance in our ADAS, which will assist the user for parking. After that, we have used a critical alarm system by using LEDs and Python dashboard. This is the very important part. We have explaining here the whole overview of our system. As we can see here, we have used STM32 microcontroller for computing, processing all the values. In the input side, we have used potentiometers and ultrasonic sensors to get the data. We have used potentiometers to generate the acceleration, brake, and SOC and motor temperature values. We have used the 3 ultrasonic sensors to get the distance information from front, left, and right. Also, we have used the alert warnings such as obstacle detected, blind spot warning, buzzer alert, or LED indicators. And at the end, we have created one Python based dashboard which will display all the values collected by the sensors and STM32 into a proper mannered way. So this is Python dashboard and simulation pipeline. We have used various technologies during this internship. So the first one is STM32 Cube IDE. We have used it to program our STM32. To configuration and ADC calibration, we have used STM32 Cube IDE to program our STM32 microcontroller. After that, the next technology which we have used mainly is PixSimLab. PixSimLab uh, helped us to simulate all the project without using any hardware. So instead of using hardware, we have implemented all this internship into a virtual simulation platform, which is PixSimLab. After that, at the end, we have used the Python dashboard by using UART serial communication to display all the collected information in a proper structured way. The dashboard refreshes every 10 milliseconds and it matches the firmware sensor polling cycle for seamless real-time visualization. The things which I have learned in this internship are I have learned how to deliver an end-to-end embedded system prototype from sensor level firmware to real-time desktop dashboard. I have learned how to design a real-time embedded system by using STM32 platform. I have also learned how to interconnect the components or interface the components to STM32 microcontroller virtually on a PixSimLab. We have implemented various safety critical systems such as ADAS and actuations like LED alarms for user safety. And we have also learned how to develop a full stack integration of firmware and embedded system. So that was about my PPT. Now I will demonstrate my project. So in STM32 Cube IDE, as we can see, here is our project EV dash. In that, in core folder, we have two folders such as INC and SRC. INC folder contains all the .h files, which means it contains all the header files, the uh, declarations of all the functions which we have used during programming is done by the header files. And after that, in SRC, which means source files, we have the main programming files. All these program files combined make our projects work very well. As we can see in our main program, we have firstly included all the .h files, which means we have included all the header files. After that, we have declared the typedef functions, and in further programming, we have declared the timers, UART for serial communication, print status for printing the values in virtual terminal, process CMD to process the data, and these are the main codes which we have used for our project building. If we want to build a file here, build a binary file, we should build the project. So as we can see, I have got zero errors and zero warning, which means our code is working perfectly fine. Now by uploading this code into PixSimLab, we will be able to generate the simulation values. So I have already uploaded the binary file into the PixSimLab. So we can see by opening PixSimLab into spare parts module, we can see all the components which we have connected for this project. So first of all, here are potentiometers, which are used for simulating the values of acceleration, brake, SOC, and motor temperature. We have used the PA0, PA1, PA2, and PA3 ports of STM32. After that, we have used the three ultrasonic sensors to get the values of distance from front, left, and right. We have used PA0, PB0, PB1 for front ultrasonic sensor, and after that we have used PA2, PA3 for left, and PB4, PB5 for the right. And at the end we can see we have connected various LEDs to display the criticalness or the alerts through the LED. Now by uh, sending some commands in virtual terminal, we are able to open this Python dashboard. As we can see, the values which are here in virtual terminal of PiximLab are as same as in the Python dashboard. So if we increase the front distance here, we will get a error or alarm in the system. So yes, as we can see, this is our vehicle in our front and it is very close. So now our system is giving us a critical alarm. If I lower this distance from the ultrasonic sensor, the red LED will go off, the vehicle will move forward, and the distance is uh, very much. So the system will give us alarm none, which means we have no alerts right now. If we increase the distance from left and right, it will take some time and update the values also in the our Python dashboard. If we increase our acceleration, as we can see, if we change the acceleration here, we can see the changes also here in EV metrics. By changing these values, we can now know that we have successfully implemented the EV dashboard system. In EV dashboard, we can indicate speed, battery percentage, mode, which is normal mode, EV matrix, in which we will get to see all the values of from every component: torque, acceleration, brake, motor temperature, alarm, fault, and signal. So uh, we have increased the distance of right ultrasonic sensor. So as we can see, here is the vehicle. It's a bird eye view, which means it's a top view of our vehicle. This is speed history. If we increase the speed acceleration, as we can see here, our SOC was at the top. That's why we are seeing this as 100%. If we increase the motor temperature by so much, it will generate a red color alert here, which means our system is working completely fine. So this is all the things which I have built in this internship. Very much. Thank you, Emertxe, for giving me this internship opportunity.